was interesting. All right, class proper begins now. Hope everybody had a good weekend. So I put up some stuff for everybody on Blackboard. Did my mic settings a bit now that I'm actually talking. So I put your midterm and your homework for up, and I sent an announcement, so hopefully we don't have to spend too much time going over it. But I split up one assignment into three things, basically, just hopefully to make it easier to keep track of what had to be done. If it's more annoying than not, let me know, and I won't do that again for you all, but it seemed to make sense. So you have three things that are due basically at the end of the month, so it's all technically homework for. So you have some group stuff and some individuals. I'm doing this backwards. Individual and some group work. It's in the upcoming deadlines. It's in the UML patterns, UML plus patterns folder. Basically, it's just some questions to answer individually, some group work, which is basically your task management type of thing for the midterm that I told you you're going to have to do. I gave you a markdown format to use for your document. So basically, commit the task to markdown, commit the PDF of your graph to GitHub, and then submit your commit ID. So I want to try this to see if it's a little bit easier to grade. And just whatever the last commit ID is basically for that. But makes it a little bit less annoying to grade if there's an actual submission. It's my end, not yours, but basically individual group work. And then on the side here is this term project thing. So basically this is just the rubric for your term projects. The deliverable for this is a PDF of your slides, basically. So remember, each team has to do a presentation for the midterm. And I've got all your talking points here. Point number 3 is your project timeline, which oddly enough is your homework 4. So they all kind of fit together. Over my office hour, I also wrote a randomizer in Python for randomizing the teams. So here are the dates that you are assigned to. If there is something horribly wrong that you just can't make it, please let me know. But other than that, I'm going to assume everybody's going to be able to work these days. And yeah, the randomizer is basically just I put you all into a Python list and called random.shuffle. And I did not track the seed, so it's not repeatable. But just basically three things do. Two of them are a group, one of them is individual. So just make sure you keep up on that. And the course information page is updated with these dates. So with that, we can talk about UML unless anybody has any questions. Okay, screen flicker. Make sure we get our diagram here. Okie dokie. Good. Oh, good. Get a meat boy going. Okie doke. So, today we're talking about UML. This is a thing which you may or may not need to use in industry. I've talked to some of my friends who are still working, and they say, oh, that's that thing I heard about 10 years ago that I've never touched since school. Or some of them use it on a daily basis. It just depends on your business. It is a thing that you have to do for modeling out your project, for basically structuring things. It's wonderful for communication and for simplifying and refining and all of this fun stuff. But the key thing is that it is contentious if you use it or not. Some of you that have worked in industry, whether you've done internships or whatnot, there's a chance you've seen it, and there's a chance you haven't. It's really hard to know because it's honestly, if it's been adopted, it's on a business by business basis. So what we're covering today is we're going to talk about basically the why of modeling, why we do it, why we care, why you should maybe consider doing it in your projects when you go out into industry. And we'll probably get into things like class diagramming. And I know that you've all probably seen class diagrams in your intro to Java class, but we're going to formalize things here. And we're going to talk about some of the other diagram types as well. And for us, we're going to be focusing on Well, there's basically two key categories for UML. There's structural and there's behavioral. Structural is your more static side of things, and behavioral is the dynamic. So structural is like implementation, attributes, methods, how implementation should probably be done. Whereas the behavioral is the communication. It's your flow of data, your flow of events, and things of that nature. So this all goes into UML. And it is contentious again. I will say it depends on your role and your perspective, but to me, it's at least a beneficial activity. And the reason why I say it's contentious is that everybody kind of understands the benefits, right? I mean, I don't think there's any downside to, coming up with some diagrams and trying to communicate your intentions a little bit better. Because think of it, not to go too far off topic here, but let's say that you are the lead designer on a project and you're trying to structure everything out. Your programmers probably all have an idea of what to do. They may all have different ideas of what to do. You may also have people who are not technically oriented attached to the project where you need to communicate with them. This is what the module is for, right? And they don't care about code. They might not even care about requirements. But if you give them a nice, like a use case diagram, right, or a communications diagram, you can walk them through, here's all the use cases. This is what this function is doing. They don't care about return types, but you can still communicate and talk with other people. Or maybe you have to refine your ideas. It's possible that your requirements are good, but when you start walking through your use cases, start walking through your various diagrams, you realize, oh crap, we're missing something significant, and we only figured that out by looking at these figures. Or you might not. But the thing is with that, let's say you go through all this effort, and I'm really trying to structure the story like you have all these models you've created. What happens if you find a problem later on down the line in your process? Well, what I've been saying from the beginning is you have to go back, right? Depending on your design methodology, agile or waterfall, you have to fix your requirements. You have to fix your implementation. You also have to update your models, and that's extra effort, which a lot of people think is maybe too much. But don't let me color your perceptions on that. I think this is a very beneficial activity, and I honestly would argue the benefit is worth the effort imparted. So why do we care? What is modeling? There are kind of four key aspects here. So we are simplifying reality. So we are taking this very convoluted project and turning it into a little set of stick figures and boxes and lines. So you can really get at the meat of whatever you're trying to show is. You also get blueprints of the system, right? So once you get further and further along the line, get closer to the structural view, you get effectively a blueprint, right? Think of like a class diagram. You're specifying your classes, your attributes, which are your variables, right? Your methods, relationships between everything here. You can pretty much take a class diagram and just build it, right? I mean, there are even tools for automatically generating code from class diagrams. So you have a nice pictorial structure of what your code looks like. But kind of the key thing is we're just trying to understand the system. Think of your hobby projects that you're working on, whether it's for fun or it's a term project like I'm making you all do. If you start out and just start coding, you're probably going to miss a lot of the nuance. But if you actually take the time to plan it out, you can just kind of tick off your checkboxes on your plan as you go, right? And if you have models of what each of these figures or what each of these modules or features or use cases, whatever view you're looking at, you have a very clear picture of what has to be done. And you can identify early on if there's a major problem with this. That saves you a lot of time in the long run, because if you get down into the weeds with implementation and you find a significant flaw, it's really hard to restructure everything. Whereas if you find it in the model level, well, you haven't coded it yet. You can just tweak your artifacts and your requirements. There is a game, going way off topic now, but there's a recent game that came out. It was a roguelike. It was one of the pretty ones. Shoot, I'm gonna have to look this up now because this was actually a really interesting example. Graphical roguelike releases. It's like Stone Shard, was that it? Yeah, this one. So, gorgeous looking roguelike game came out recently, right? So it's very pretty. It almost looks RPG Maker-esque, but it's like a deep role-playing roguelike type of game. There's no save function, as my understanding, or there's like limited save capabilities. And the articles that went into it were basically that they didn't think anybody wanted it, or they forgot about it. And then when they went to go code it up, they couldn't actually add it in because it would break everything. So if that had been caught early on, like a use case would be save game, right? That was never featured in the process, to my understanding. So you can kind of get a feel for like the features that you need over time and build it into your system. And the reason why this is like problematic for roguelikes is everything being procedurally generated. My guess is they had randomization just all throughout the game and it wasn't tied together in any way or something of that nature. So that's like the purpose of modeling, just to refine our ideas, to get it on paper and to get an idea of what's going on. We look for 4 aims with modeling. So visualization, I've talked about, right? Specifying structure and behavior, I've kind of talked about. Templates for constructing the system, that's your structural implementation type diagrams, right? So we're figuring out how to build the system. We also have documentation. This is a software artifact, a model. You can link it to requirements. You can link it to implementation details, to test cases. Basically, these models can act as living documents in your system. Use them for auditing purposes, use them for customer follow-up, whatever you need to communicate with, you have a rigorously developed set of models that you can talk to if you ever need to describe something or provide traceability that this is why this decision was made. So it goes back to this whole documentation being important thing, really. It's what makes you a real software engineer instead of just somebody coding for fun on the weekends. You take this seriously, you follow a rigorous process. To me, that's an engineering behavior. So we have this notion of modeling for software, right? Class diagrams, use case diagrams. You've seen use cases in class diagrams probably before. There's a ton of other models we can use, which we'll get to. But I'm curious, do any of you, can you think of any models that would be used outside of software engineering? So let's say that we are building a house. We are building an engine, right? We are building something, play structure out in the yard. We are rezoning a neighborhood for office use or something. Are there any models for these domains? Let me know if the question doesn't make sense. Basically, I'm trying to get you to think more broadly, right? So we focus on software in here, but there are a ton of other domains, engineering domains, science domains, business domains. Does anybody else have models for their work? A legitimate open question to you all. I need to figure out how to get the TTV emotes into Streamlabs. Engineering uses would be CAD modeling for something like engines. Hey, absolutely. That's a blueprint, right? So that is a form of model. So your architectural diagrams for buildings, these are models, right? We may have business processes that we have to follow to scope out a project and sell it to somebody, right? There's going to be a set of probably visual diagrams on how we can handle that. CAD drawings is actually the example I was going to use. Yeah. Oh yeah. Not even building buildings, right? If you have to 3D print something, you have to make a CAD model. What is a CAD model but lines on paper with units attached, right? And how things interact. Later on, we're going to talk about assemblies and components. I'm going to relate it to 3D modeling. There is relationships in these models for how, friction, like what frictions are applied, how things are linked together. There's modeling everywhere, basically. And kind of what I'm going to steer you all towards here is that the UML process we talk about here in class, they really can apply to any domain, which is really interesting, if you think about it from an engineering perspective. We have a process that is not limited to software. And to me, it might be painful to do on a daily basis if this is, part of your job, but you have something that's really domain independent and it can be used anywhere. What does that mean? Am I saying it's some aha moment? Well, pretend like you are in a meeting and you're the only software person there, but you have electrical engineers, you have civil engineers, you have construction workers and project managers, and they all understand UML to a point. You can talk the same language rather than going in circles about what your own particular knowledge base is. Everybody can talk the same thing, which means you can make progress. Right. So one of the other things here with these 4 points is that do we have, is there one UML model that will cover every single one of these? Not necessarily, right? Constructing a system we're not going to do with use case diagram, but we probably will with class diagram. Or class diagrams are not necessarily going to tell us behavior, but communication diagrams will. So the point is we kind of have these 2 high-level constructs. There's the structural and the behavioral, and we'll decompose it into other types of models. They all have a specific purpose, and they all show a particular view of the system. Now, there are a ton of these. You don't have to know all of them. We're going to cover some of the high-level ones, basically. But first and foremost, let's start with what UML is. So this is the Unified Modeling Language. I can't remember if I spelled that out yet or not. But basically, this is a process-independent, language-independent modeling language. And because it's a language, that means it has syntax and it has semantics. So basically, all the lines and all the boxes and all the ovals, they all mean something specifically. Interestingly, and I'm going to go off topic a little bit here. So there are 3 people called the 3 Amigos in whatever articles you read. Basically, there are 3 researchers here that each independently came up with a variant of what UML became. So there's the Booch method, there's the object modeling technique, and then there's object-oriented software engineering. And these 3 guys, these 3 amigos, I've got a picture right here of all of them, they came together, and rather than working in their own little silos, which happens all too often academically, they came together and they put together this UML specification. Basically, they took each method that each person's research group was working on, and they formed a formal specification. So that is interesting in and of itself because academics tend to not go outside of their own research groups. But these guys actually accomplished something really interesting. So they ended up with this, let me pop over here, uml.org, came up with this UML specification. At 20 years it's been out since UML 1.1, this has basically revolutionized software engineering, and it's incredible. And Grady Booch has a very interesting picture. Now, it's not the clean-cut, not images. A little bit less formal and more crazy older professor style, but definitely with some of the bigwigs in software engineering, which is pretty interesting, I think. So let me scroll through here. So UML, it is process independent, right? So you can use it for waterfall, you can use it for agile prototyping. It fits better with the more incremental ones, right? It fits better with something that's more iterative like waterfall. Can you use them for agile? Absolutely. Can you use them for prototyping? Yes. Can you use them for spiral? Yes. Can you use it for hobby project on the weekend with no process? Yes, absolutely. You can even use it for electrical engineering if you want to go to another domain. It's possible to coerce it there. The interesting thing about this, again, it's independent. It gets all the ideas that you need out there in a very nice visual format. One of the things I should probably mention too I'm not expecting you all to become experts on the UML language, right? This takes a lot of time and effort and practice, but I am expecting you to at least be able to come up with a reasonable facsimile of a UML diagram. So if I ask you for a class diagram of something, you should probably use approximately the right line types and arrow types and box types and all that, right? Like you shouldn't give me a hexagon and call it a class. Nobody's going to know what that means. The problem with something like UML is that there is a specific syntax here. You've never done UML before, so no worries. You're going to get it all right now, so don't worry. A lot of people got it in the Intro to Java class. That's kind of why I'm saying you may have seen class diagrams before. But the thing is that like the different line types mean different things. So when we talk about relationships in a little bit, you're going to see dashed lines versus solid lines versus lines with arrows versus triangles on the end of arrows versus diamonds. They all have particular meanings. And the same thing goes with the box types. Like the class diagrams are rectangles generally with a bunch of information in them. Hexagons mean something very specific to other parts of the diagram. So just be aware that you can't just like throw boxes on paper and call it a day. You actually have to think about what you're putting in there. They're just kind of like you all more or less understand what I'm saying because it's English. If I started speaking in German, a lot of people would probably get lost because you're not expecting it, or it's the wrong language for the context of the class here. Or I started making up a language, for instance, would maybe be a better representation. But yeah, just you don't have to be perfect. Just get as close as possible as you can. That's all I'm asking. Oh, that was the other thing. So the reason why I'm mentioning that is that if you start doing a lot more UML and you want to use some of those really nifty automated tools that are out there, like you can automatically generate code from class diagrams. You can generate class diagrams from use cases. You can do a whole lot of automated generation, which a lot of engineers really like because it saves you time. It basically gives you stubs or prototypes or whatever you're getting. That language has to be good because the tools are expecting it. Usually there's no flexibility in an automated tool. And if that's something you're interested in, there are a bunch of plugins for Eclipse. For instance, there's some websites out there too, which are I've not had any success with myself. But like you can generate a class diagram, pop it into like do it in Eclipse in a particular tool. There's like Argo UML or Visual Paradigm. There's a few other ones that are out there, but basically they're Eclipse plugins, and they will help you with that syntax. Not too far off the rails, I hope. Anyway, so what is UML? We have 3 building blocks in UML, and they're all important. I'm going to pop them all up here. So first of all, we have a thing, which is a very appropriately named object, basically. So a thing is a first-class citizen in a model, and what does that mean? That's a very software engineering-y term, first-class citizen. That just means it's prominent in that particular model. So if you have a class diagram, the class is the first-class citizen. If you're building a communication diagram, it's going to be the objects that are talking. And if you're building a use case diagram, it's the use cases. Basically, that is your thing that you're trying to model, right? It's the focal point of the model. The relationships are basically the lines that you draw to tie things together. It's how things are related to other things. So if I have a animal class that I define, and I want to create a subclass for a dog and for a cat, and for a mouse, for a human, right? We're all animals. They would have relationships to the parent class. They'd have a special relationship, which we'll talk about too. Last but not least, we have the diagram. So this is what ties things and relationships together. That's your class diagram, your use case diagram, your X diagram, basically. There's a bunch of them, which we'll get to as well. So UML, currently we're at 2.5.1. They specify 2 different types of diagrams. Again, structural and behavioral, static versus dynamic, if you want to think of it that way. Basically, these are just different views of your system. And we'll talk about a little of the structural diagrams and a little bit of the behavioral diagrams. All right. So here is the meta model of the UML diagramming models. And a meta model is a fun thing to talk about as a software engineer because a meta model specifies how a model is to be made. So here's basically just a viewpoint of UML. So we have structural and behavioral diagrams. Under structure, we have our class diagrams, which we'll be talking about soon, object diagrams, which are basically just instantiated class diagrams. We could have composite diagrams, which show how things kind of fit together, deployment diagrams, which show how you can express software into actual hardware, package diagrams, which lump things together into packages. Basically, all of these different diagrams here are showing you different viewpoints. All right, so that's your structural side. The other half of the tree is your behavioral diagrams. This is where you show interactions, collaborations, data flow, this kind of a thing. We've looked at use case diagrams already, right? So you should be familiar with that at this point. We're going to look at a couple of the interaction diagrams, so sequence and communication. Basically, we're showing paths of execution in a way, so function invocations. We're showing how data is flowing from one point to another. We'll be getting to this honestly, but basically you're kind of showing program flow. What else do we have here? Well, we have state machines. If any of you have ever done a state machine before, like you have a starting point, and then you have an initialization state, and then you go to the main menu state, for instance, and then the gameplay state, or it's basically just showing you the different states that your system can be in. And with that, how you can get from one state to another. Now, let's say you have a phone application. I have a start state, so I start by turning the program on. Then you have to log in, so the next state is log in. Well, how do you get from start to log in? You have to open the application. How do you get from login to account overview? Well, you have to log in correctly. And if you don't log in correctly, you go to another state. So basically you have like guards or constraints that tell you how you transition from one state to another. And that informs your coding, right? So how do you launch the main menu screen? All of this has to have happened first. How do you launch the account management screen? Well, you need a cookie or a token that says that you're logged in successfully. State machines are kind of fun. They're a nice way to think about how your system should be performing. We're not necessarily going to talk about them as much. We may later if we have time, but they're kind of a helpful thing. We're going to mainly focus on sequence and communication diagrams. Actually, we're going to focus on these diagrams in total. So here we have our class and our object diagrams. So these are going to be the structural things. We're going to get to class diagrams a little bit today, and the rest of them later on today. Under this line that I'm kind of pretending exists here, these are your behavioral diagrams. So use case diagrams, technically behavioral, right? So they're under the behavior branch of the tree. Because you're seeing basically behaviors, right? Those are those verb noun use cases, log in, generate level, clear screen, use cases, right? They're really demonstrating a behavior or a feature. Then sequence and communication, we'll get to this basically. There are two different types of models which show basically flow. So if you need a visual, here we have them highlighted for you. So we're going to start with class diagrams. But we're actually going to talk about class diagrams in terms of relationships because they're great for demonstrating them. Now, one of the central tenets of UML is the relationship, right? I think I showed that on the first slide. There was things and relationships and diagrams. Relationships will exist in all UML diagrams. They all kind of feature in class diagrams, which is why I'm going to show this. But keep in mind, you can really apply these anywhere, not just here. So what is a relationship? It's a line between two things. It's technically a path. It can have different like monikers on it. It can have constraints, can have multiplicities, which we'll talk about, like how many of one thing exists. They give you a lot of information, some of it for implementation, some for your information or for communication purposes. All right, so we have a bunch of different views at different points here. These are all the relationships that we'll be talking about for UML, and basically we're going to go through them one by one here. So if you have never seen a class diagram, this is what one can look like. So here we have a class diagram for, it's a class diagram, but call it a seminar, and then you don't have to repeat the word class multiple times. It's a course, basically. So here we have a formalization of the various classes that you would create for this type of system. So you'd have a student, you'd have enrollment, you'd have a professor, and a seminar, right? So here's your classes. Why are they classes? Well, they have attributes, meaning like variables, right? They have functions that you would call for that class. So on here, you would like basically, if we were making banner or whatever, whatever system a university would use, we need a way to represent a student. We need a way to represent a professor. We need a way to represent the various courses. We need to figure out what that student's enrollment is in the class. And there's a ton of other features we need as well, right? But this is a simplified view. The relationships that we're focusing on here, these are your lines, right? So some of them have arrows, some do not. Some have numbers on them, some do not. Some have text, some do not, right? So this is all the different kinds of relationships we have. Here we basically have a dependency. Or it's a directional association. The dependency would be a dashed line. We have the, like, if we have one student can be enrolled in one or more seminars. We have a professor. Either 0 or 1 professors can be attached to a seminar. It's possible a seminar doesn't have an instructor. Maybe it's a student-led type of thing, right? Students, professors have personal information, name, address, phone number, email. Are you eligible to do enrollment? Seminars have names. Seminars can add and drop students, right? So you're basically trying to get a feel for the different attributes and methods that a class will have, or an object will have. We're going to get to all of this kind of stuff here as well. So if this looks a little bit convoluted, don't worry, we're going to get through all of it. Let's step back for a second. We did use case diagrams already, right? And we didn't talk about UML. Or I said, this is UML, get used to it. Why did we do that already? Well, you may ask, we do that to do an early identification of what our system needs to be doing, right? So early requirements elicitation or requirements refinement. Well, what do we do with these use cases now that we've gotten our requirements spec all formalized? Well, it can inform your class diagram. So remember I told you, I'm going to flip over to my kind of ham-fisted game example here. Here's a simple use case diagram. No actors, right? No associations. I just did this quick before class, but use cases are verb noun, right? Start game, generate level, save game, get high score, whatever it is, verb noun. Okay, that's important here because nouns, these could be your classes. Verbs could be your method, right? So if I go back, I would have a game class, for instance, right? One of the methods then would be start. So if you go to, let's see, right here, let's pretend this is my video game example. I would have class game, method start, or method save, or method clear, or, right? So you can actually take this and start building your class diagram from it, which is kind of an interesting usefulness for this thing. And is it perfect? Are we done with our class diagram once we translate it? Well, no, you have to refine it, right? A game is going to have levels, so I need to have a level class. Class level will have a generate function, probably a bunch of attributes like the data for the level, maybe the objects that are in there. How wide is it? How tall is it? Is it 3D or 2D? Right? So whatever variables you need to describe this thing, again, you can start seeing hopefully what the process is. Generate level tells me, not a whole lot programmatically, but if I add in a class diagram, so level. So here we have some boilerplate stuff in draw.io, sorry, diagrams.net now. Method generate. And I'm going to say it's a void, and maybe it returns level data. So I'd have another level data class, or might just be a array 2D. Well, I might have level data, which is tied to this particular level. It's an array 2D. I might have monsters, which could be just an array. And I think I can just do this. Yeah. Right, but I probably also need an initialize and a destroy. We don't show that in the class because it's common knowledge. But maybe we have a modify xy type, and it's a null return or a void return. So from this very simple use case, I start generating a class diagram. Well, with this class diagram, maybe scroll over a little bit here. I'm just kind of going by the seat of my pants. I honestly don't have a an end game here or an end goal. So let's say I've got my levels. This is going to be an array. I'd call it a Python list, but I'm trying to hopefully remember my Java syntax a little bit. And we have what our start, void. I did UML in 163. That's good. So kind of what I'm getting is that some of you have and some did not. So I'm at least going to talk about it a little bit for this. Right, but here, all right, so we have these two classes. The important thing is we need a relationship, right? So I'm going to have one game. So I have one game object. And then I'm also going to have one dot dot infinite levels. So let's call this a procedurally generated game that never ends. Okay, so it'll be a high score type game. I'm going to have levels tied here. So I'm going to have one game instance. And then I can have any number of levels. And I can add more and more and more and more information as I go, right? But from these two use cases, I'm starting to generate my code in a way, or at least the blueprint for the code. So that's the whole point of figuring out what you're building and what the relationships are. Right? Use it for a brainstorming type of thing. Hopefully this is kind of making sense and where the usefulness and the power can come from. Like in your team meetings that you have weekly, right? You're probably talking about how you're going to work on the next feature and all that. And if you're sharing your screen and live coding, like I've seen a lot of you jump into live sessions. I haven't actually watched them because that'd probably be a little bit creepy from my perspective. I don't know. If you want me to join, just always ping me. But like it's a lot easier to talk about a feature if you have something high level like this, right? Whereas if you're coding, you're kind of like doing over the shoulder kind of thing. I'm not saying you shouldn't do that, just different purposes. All right, 10 minutes left. Let's get through the relationships at least. So now we're actually going to talk about the different types that exist in UML. First one is a dependency. So this is where that syntax starts coming into play. Here we have a dashed line and an arrow. So dashed is important, arrowhead is important. A uses B. And what does use mean? B is a local variable in A, B is a return type, B is a parameter type, A uses methods in B. So actually, let me fix my model here. This should be a dashed line with an arrow at the end. Arrow, please. Arrowhead. Can I? Really? Or is it just hiding? What's going on here? I don't have an arrowhead. It should have an arrowhead. Oh my god. Okay. Am I blind? I feel like I'm blind. Let's just do this then. All right, well, why do I need this dependency here? Make you dashed. All right, there we go. Well, levels is going to be a local variable in A that we have here, right? So this game has a dependency on my level class because I'm going to generate levels. It's going to go into my local array. Programmatically, or I guess extra effort, absolutely, but you can very easily feed in that I have an instance being pulled in of B into A. Or I'm using methods in B, or basically, again, there's a dependency here, okay? but dependency dash twine with an arrow. We can also generalize things. And this is something that tends to be more specific to the object-oriented approach. You can do it in procedural or more standard, non-OO types of designs. But this is where you have a superclass. So you're not your God class, but basically it is a kind of a general construct that you're going to specialize out to other classes. So the common example with this is your superclass or your parent class would be animal. And your subclasses would be more specific, so dog, cat, mouse, elephant, human, otter, naked mole rat, whatever you're trying to model here. They each have very particular specific characteristics, but they have a general kind of commonality at the top. So superclass, subclass, parent class, child class, whatever you want to call it. This is your is-a relationship. Solid line with a triangle. It's a filled white triangle. So again, importance of syntax right here. If you give me this kind of a line, I will know exactly what you mean. So that's your is-a. You can also do this for, like I've got an example with cars. So truck is a land vehicle, or biplane is a airplane. Specific characteristics, but every airplane will have wings, it'll have an engine, it'll have seating, whatever you're trying to model here. And why I said that this is more object-oriented, but you can do it anywhere. You probably have done this in Java. If you, in your Java class would be my guess. You can do it in Python. Python has classes. You can do it in C++. C++ has classes. You can do it in C if you add some coding trickery to make yourself have classes, but basically it's all like pointer math and pointer trickery. So it's possible. I'm sure you can even do this in Lisp if you really wanted to go with that route, but it's a useful design pattern to have. So generalization, honestly, it's more for like aggregating code so you're not using the same variables over and over again. Everybody just inherits from one set. We also have associations. So this is a solid line with no arrows. It's intended to be bidirectional. You can have an association with an arrow, and this is where the distinction between dependency and association exists. So here we had dependency, dashed line. Association, you can technically have an arrow on here, but without one, it's intended that it's a bidirectional relationship, meaning it goes both ways here. Now, what do we do with this? It's not just that they're related to each other. I mean, that's what association is at its core. But you add a bunch of designators on this line, right? Like we added the multiplicity of 1 dot dot asterisk or 1, or we may have constraints or wording on here to tell you what the relationship is or what the role of B is to A, and there's a whole lot of things that we can add here. So here's an example of multiplicity, and I got to figure out why my... All right, just Hangout's going nuts. Here's an example of multiplicity. So here we have two classes on the left and the right. We have an association between each, and we have a multiplicity here. So one department can have one boss. Okay, so that's what this means. An employee can have any number of children. A boss can have one or more employees. So basically here you're trying to capture how many of this object are related to the other object. So the asterisk basically means unbounded, or it's infinity. Think of it just like a range that you're specifying here. You can do 1 dot dot 2. That means this boss can only have 1 or 2 employees. But basically it goes on the association line. It's a number. Everybody knows that one employee will have 0 or more children, for instance. Or a game will have 1 or more levels. For my example that I did over here, right? So one game's gonna have 1 or more levels. You can even put it on the dependencies too, by the way. So this is the directional side of the association. In this case, it's not necessarily bidirectional. It's more of a has-a type of relationship. So A has something in B. So for instance, B is going to be like a local variable type. Kind of similar to the dependency, but we basically are pulling in the whole thing. My God, what is going on? Did like something explode? All right, nothing important. Sorry, should really turn my phone off. All right, so we have directional and we have associations. Now we talk about the trickier ones. So there's aggregation and composition, and I'll probably run out of time after this. They are both represented by a solid line with a diamond. Aggregation is a white fill, composition is a black fill. And the way you think about these is who is in charge of the objects. So both of these relationships describe making basically like an assembly out of parts in a way. So like to go back to your example of a CAD model for 3D printing, you would have a bunch of separate parts in that model, right? So if you're building an engine, it's a good example. You have pistons, you have the housing, you have the spark plugs, you have all the bolts in there, you have all the chambers. So basically it's a series of parts, right? And you put them together and you get a assembly or a composition. Basically you get your whole thing is the engine, right? That's the idea between aggregation and composition. You have whole and parts. The key difference, though, aggregation is logical, composition is physical. The way you think about it is composition, let's say this is an engine and this is a part. The engine is responsible for instantiating and destroying each of the parts. All right, so if I want to build an engine in software, I would have an engine class. The engine class would create all of its parts and bring it inside itself. It's the physical, I'm only ever part of this engine. Whereas the aggregation, the parts can be self-sufficient, right? I can kill off the engine object and the parts will still exist in memory and I can use them elsewhere. Slight distinction. The term is syntactic sugar, I guess. They describe the same thing, just who's responsible for the objects in memory is basically kind of the clear distinction here. Let me know if that doesn't make sense, because I'm happy to expound on it, but think of it in terms of creators and like instantiators and destructors, or constructors and destructors. So to take that and turn it into maybe some examples, which are hopefully helpful. So generalization, is a kind of. So cardinal is a kind of bird. Blue jay is a kind of bird. Animal is a type of mammal, for instance. Truck is a kind of land vehicle. Land vehicle is a kind of vehicle, because you have seagoing vehicles and whatnot. So generalization should make sense, hopefully. Aggregation and composition are where it gets tricky. So aggregation, a wheel instance is a part of a vehicle instance, but once that vehicle instance goes away, the wheel does not. Wheel still sticks around. Composition, you might have a door instance. That's only ever going to be part of this particular vehicle instance. So if that doesn't make sense, hopefully it will over time. Or if you have questions, again, feel free to let me know. We will end here on this scanned figure, where this is, again, kind of a school-related diagram. Here we're just showing off various associations that you have. So we have your aggregation, you have your composition, we have multiplicities, we have some wording on the actual lines as well, which can be helpful for you. Right, a school having a department doesn't necessarily help you programming, but it helps you if you're communicating, right, or understanding the model. So here's kind of a good example of aggregation versus composition as well, to kind of wrap up here. A student can be a member of a school, right? So we have an aggregation here. But if the school goes away, the students still exist, right? You don't die if your school folds. Whereas a school is going to have a bunch of departments, right? One or more departments. But if the school disappears, so does the department, right? There's only ever, these departments only exist when the school exists, whereas students will always exist, even if the school closes down. All right, so we have hit our 150 mark. Does anybody have any questions, comments? Anything you need to chat about before we end here? Again, check on the assignments, make sure that you get going with your team stuff if you need to. It probably will take you a little bit of time. I don't want people scrambling at the very last minute. So, other than that, I'm going to see whatever fire is going on in my my Hangouts, so that I probably should have muted my desktop audio so you didn't hear the bleeping the whole time, but oh my god, what's going on? Okay. Dr. Moore and DeVries are complaining about something, which is fairly common. Alrighty. You all have a wonderful day. I will talk with you all on Wednesday, and we'll keep going with UML. So, have a nice and sunny, yet maybe slightly chilly day, and enjoy it before the snow starts coming.